Hello my friends, and welcome back to the You Can Do TV channel. Foot launching a rigid-wing glider like the Archaeopteryx requires a careful combination of pilot skill and aerodynamic design. In this video, we observe how a pilot prepares for and executes a successful foot launch from a mountain slope. The process begins with positioning the glider on an inclined surface with enough elevation to reach the necessary liftoff speed, similar to delta wing hang gliders. Thanks to its lightweight structure and efficient wing design, the Archaeopteryx does not require wind for takeoff when launched from steep terrain. Pre-launch steps include checking control surfaces, connecting the harness, and balancing the glider against shifting gusts. As the pilot accelerates downhill, the airflow builds beneath the wings. Once sufficient lift is generated, the glider separates smoothly from the ground. This aircraft is built not just for foot launching, but also for winch, bungee, vehicle, and ultralight tows. Its adaptability to various launch techniques makes it a rare example of engineering versatility. After takeoff, its impressive climb rate allows quick elevation gain, even in weak thermals. At just over 4 meters in length and weighing around 80 kilograms empty, the Colomban CriCri MC15 is the world's smallest twin-engine aircraft. In this video, we follow the preparation and solo flight of Feats, a model piloted by a skilled aviator. Before takeoff, the aircraft is inspected for engine function, control surfaces, and fuel levels. Its lightweight structure, made entirely of aluminum, enables it to achieve a maximum speed of 220 kilometers per hour in its thermal version, and up to 283 kilometers per hour when electric powered. Each of the two engines delivers 11 kilowatts, supporting strong performance despite the plane's compact form. The wing loading is 55 kilograms per square meter, and the airframe is rated for load factors of +6 grams and -3 grams, giving it the maneuverability needed for precise solo flights. The glider's name, CriCri, is a nod to designer Michel Colomba's daughter, Christine. While small in scale, it requires the same pre-flight checks and discipline as any larger aircraft. This footage captures the end of the first flight stage. With a wingspan just under 5 meters and an elongation of 7.74, the CriCri demonstrates how ultralight aviation combines technical efficiency with the pure joy of flight. Take a behind-the-scenes look at the flight of the Hungarocopter HC-02, captured on a summer day in Verpillet. This video follows the aircraft from ground preparation to mid-air maneuvers, offering insight into the operation of this light helicopter. The journey begins with the pilot, Farkas Gabor, preparing the helicopter for takeoff, ensuring that all systems are functioning properly. The pre-flight check involves a series of inspections, including the engine, fuel, and safety systems, to guarantee a smooth and secure flight. Once cleared, the helicopter lifts off from the ground, offering an aerial view of Verpillet and the surrounding area. The pilot skillfully maneuvers the aircraft through various flight paths, demonstrating the agility and stability of the HC-02. Throughout the flight, the pilot remains focused on maintaining control and safety while providing smooth transitions between maneuvers. As the flight progresses, the video captures stunning views of the landscape, showcasing the versatility of the Hungarocopter HC-02 for both recreational and professional use. This video offers a close-up look at the thorough preparation and skilled piloting required to operate such a unique aircraft. The journey starts with engine warm-up, thorough gauge checks, and safety verifications. The helicopter lifts off smoothly, ascending steadily with a light fuel load. Flying at low altitude helps minimize noise and provides clear views of the transition from suburban neighborhoods to more open terrain. As the aircraft approaches the local airport, the scenery shifts, highlighting the contrast between ground-based and aerial travel.
Area traffic, helicopter 630, Mike. Lima has a beam of 3 lakes. We are inbound landing at the airport for fuel.
A brief helicopter commute transforms an ordinary journey into an efficient and captivating experience. What usually takes 45 minutes by car is reduced to just a few airborne minutes, offering a unique aerial view of the landscape below.
Aviation 1746 Zulu. Wind 210 at 05. Visibility 10.
The flight begins with the helicopter already prepared for departure, and a GoPro mounted between the rear seats records the entire process, capturing both the cockpit activity and scenic surroundings.
Helicopter 0 Mike Lima will be crossing the runway low level midfield. I got the aircraft and the taxiway on site. I'll be behind you.
Upon landing, the helicopter is positioned for refueling and temporarily parked at the transient area. The pilot skillfully navigates through light air traffic and prepares for the next leg of the journey. Attention remains on safety and efficiency throughout the flight, with insights offered into key aspects of helicopter operation.
And 0 Mike Lima, clear the runway.
This video offers a behind-the-scenes look into the world of helicopter commuting, demonstrating how technology, skill, and planning come together to create a seamless and elevated travel experience. It reveals how a simple route can be reimagined through the lens of modern aviation.
And here we are for fuel.
Soaring silently above the Earth, this lightweight glider is a rare blend of engineering and flight freedom. In this video, we explore the operation and design of the Archaeopteryx, a highly sensitive, rigid-wing microlift glider designed for both powered and unpowered flight. With a total wingspan of 13.6 meters and an empty weight of just 61 kilograms, the Archaeopteryx belongs to FAI Class 2. It's capable of self-launch with an electric drive system weighing 23 kilograms, or it can be towed aloft using a winch or aerotow method. Maximum takeoff weight reaches 191 kilograms, and with a climb rate of 2.5 meters per second, it offers efficient vertical movement even in weak thermal updrafts. Takeoff requires only a 50-meter run. Once airborne, it maintains a minimum sink rate of just 0.5 meters per second, with a glide ratio of 28:1, comparable to high-performance sailplanes. The glider operates smoothly between speeds of 30 to 130 kilometers per hour, and its minimal turning radius is only 15 meters, similar to a paraglider. Assembly is straightforward. The rigid sailplane frame is designed for quick rigging and disassembly, making it practical for solo pilots. In this footage, the pilot prepares the wings, secures the control system, installs the electric motor and battery pack, and completes the system check before launch. Every component is designed to be ultralight yet structurally robust. A key advantage of this aircraft is its adaptability. It can be flown in open or enclosed cockpit configurations, depending on weather and pilot preference. The rescue system weighs only 5.5 kilograms and adds an extra layer of safety for high-altitude flight. With a maximum aero tow speed of 100 kilometers per hour, it remains stable under tow. Even in strong crosswinds or turbulent thermals, it maintains precise control. Once in the air, the pilot uses thermals to gain altitude, gliding with minimal energy loss. The aircraft's aerodynamic shape allows it to soar silently across long distances, with minimal environmental impact. Whether flown manually or assisted with an electric drive, the Archaeopteryx showcases what's possible when advanced aerodynamics meet minimalism. It's more than a glider. It's a precision tool built for exploring the sky with grace, efficiency, and technical mastery. Flying an autogyro may seem straightforward, but mastering its behavior requires precision, awareness, and smooth coordination. This video offers a rare view into the techniques and processes involved in operating this unique type of aircraft. It begins with a detailed pre-flight inspection. The rotor blades, control surfaces, and engine are carefully examined to ensure every component is functioning properly. Attention to detail at this stage is crucial for safety and performance. Once in the air, the video captures the autogyro's distinct flight characteristics, its ability to remain stable at low speeds, handle tight turns, and descend gently without engine power. Each maneuver is deliberate, demonstrating how balance, airflow, and rotor behavior interact during flight. Multiple angles show how the pilot maintains situational awareness and manages control inputs with finesse. The aircraft's sensitivity to changes in pitch and yaw becomes evident, especially during turns and landings. Additional segments explore low-level flying and short-field takeoffs, showcasing the autogyro's adaptability in confined environments. The footage highlights how the aircraft can operate at slower speeds than conventional planes, making it suitable for surveillance, training, or recreational use. Transitions between straight flight and steep climbs are shown in detail, with commentary explaining the aerodynamic forces involved. There's also a close look at how rotor inertia plays a role in auto-rotation during descents, giving the autogyro its signature glide. This footage provides not just a flight demonstration, but also insight into the discipline and technique required for safe autogyro operation. It highlights the unique dynamics of rotorcraft flight and reinforces the importance of preparation, judgment, and post-flight care. What happens when both the main and reserve parachutes fail mid-air? This video documents a rare but terrifying skydiving incident, offering a real-time glimpse into the critical seconds of malfunction, decision-making, and survival. The footage starts just before the jump, capturing what seems to be a normal skydive. However, things quickly spiral out of control after the first spin. The main parachute deploys, but immediately tangles around the jumper's leg. With no way to untangle it, the decision is made to cut away and deploy the reserve. But the reserve also becomes entangled, leaving the jumper upside down and trapped in the lines with no functional canopy. As the body spins uncontrollably, visibility is lost, and unconsciousness becomes a real threat. The jumper fights to stay aware, grabbing the tangled lines in a desperate attempt to stabilize the canopy. Despite being upside down with one leg trapped, the reserve finally opens, partially stabilizing the fall. The impact with the ground is severe. The jumper lands on their back without a flare, still entangled, suffering from a sore body, whiplash, and multiple bruises. Yet, survival is credited to the remaining altitude, quick decisions, and sheer determination to keep trying, even when hope seemed lost. This video isn't just a dramatic account, it offers a rare perspective on malfunction scenarios, illustrating how tangled lines, inverted positions, and partial deployments can escalate risk. It's a sobering reminder of why altitude awareness, emergency procedures, and mental resilience are critical in skydiving. Situations like this also highlight the importance of training for low-probability but high-impact events. Even experienced jumpers can face failure modes that no textbook can fully prepare them for. Imagine skimming just above the lake. The Mosquito XE ultralight helicopter cuts through the sky. The thrill of flying low and fast is unmatched, but what does it take to make such a flight possible? As the helicopter takes off, the pilot carefully manages the controls, ensuring smooth and stable liftoff. The lightweight design of the Mosquito allows it to ascend rapidly, offering a unique sense of freedom that few other aircraft can provide. With its powerful engine, the helicopter reaches impressive speeds, making it perfect for swift flights across vast areas. Flying low over the lake, the pilot adjusts the throttle and cyclic controls, guiding the helicopter with precision. The rotor blades, designed for maximum efficiency, work seamlessly with the engine to provide both speed and maneuverability. The agility of the Mosquito XE allows for quick turns and sudden altitude changes, making it ideal for exploring the landscape from above. The sound of the engine fills the air, a reassuring hum that echoes across the water. As the helicopter glides effortlessly, the pilot monitors the instruments, adjusting flight path to maintain smooth navigation. Every movement is calculated, creating a perfect balance of control and speed. The helicopter dances through the air, a testament to its precision engineering. Throughout the flight, the pilot maintains constant communication with the aircraft's instruments, monitoring vital systems to ensure everything is functioning smoothly. As dusk falls, the Mosquito XE continues its flight, demonstrating not just speed, but exceptional stability at low altitudes. This helicopter's unmatched capabilities impress those who experience the thrill of a low and fast flight. The Mosquito helicopter is put through its paces in this thrilling test flight. Before takeoff, the helicopter undergoes a series of thorough pre-flight checks. The pilot inspects the control systems, ensuring the cyclic and collective are responsive, while the engine is primed for optimal performance. The rotor blades, crafted for maximum lift, are carefully examined for any signs of wear or damage. The pre-flight checks also include a detailed review of the fuel system and safety mechanisms, ensuring every component is in perfect working order. As the helicopter lifts off, the pilot closely monitors the instruments, ensuring all systems are functioning as expected. The lightweight design of the Mosquito allows for quick ascents, making it ideal for tight, precise maneuvers. The test flight involves a range of scenarios, from hovering to high-speed maneuvers, demonstrating the helicopter's agility and stability at varying altitudes. Throughout the flight, the pilot collects data from the onboard systems, which will be analyzed to ensure the helicopter's performance meets rigorous standards. As the test concludes, the Mosquito is safely brought back to the ground, where a final inspection takes place. This comprehensive process ensures that the helicopter is ready for regular flight operations, providing a seamless flying experience. In this detailed inspection of an old AN 1300 wind turbine, we dive into the technical process of assessing its components and ensuring optimal functionality. The process begins with a thorough examination of the turbine's key systems, such as the cable loop, yaw brakes, and the top platform. One of the first issues noticed is that the heaters aren't working, which could affect the performance of various components during colder weather. As the inspection continues, attention is directed towards the bearing of the anemometer, which is found to be through, indicating wear. The control unit is then connected, and preparations are made for the rotor lock, ensuring everything is securely in place before further checks. The rotor lock is then prepared, and the turbine is pitched slightly to accelerate idling. Next, the brake and locking pins are set into position, and the pins are secured. With access gained to the hub, the inspection moves on to identifying any unintended movements caused by worn joints. The hydraulic system is activated, and the pitch decoders are tested to ensure they are functioning properly. Afterward, the rotor lock is disengaged, allowing for high-speed coupling. As part of the final steps, active stall turbines are pitched first to 0 degrees and then opened, followed by applying the brake to prevent backward rotation. At this stage, the wind is about 6 meters per second, approximately 22 kilometers per hour, which is relatively calm, but the turbine continues to generate power at approximately 200 kilowatts. Despite some wind noise, the process is carried out thoroughly, ensuring all components are thoroughly tested for continued reliability. The turbine's braking system is then checked, ensuring smooth and responsive function under load. The hydraulic system undergoes a final test to ensure optimal operation, while all electronic systems are verified for accuracy. After completing the checks, the turbine is ready for safe and efficient operation. The final inspection ensures that all safety features are intact and the turbine is capable of performing as expected in operational conditions. The first flight of the offers a rare, unfiltered look at the complexities involved in one of the world's most challenging airstrips. Lukla Airport, officially known as Tenzing Hillary Airport, is one of the most dangerous airports in the world due to its unique geographical and structural challenges. Located at an elevation of 2,845 meters, 9,334 feet, in the Himalayas of eastern Nepal, the airport serves as the gateway to Mount Everest. Its short runway, steep gradient, and surrounding terrain make both takeoff and landing extremely hazardous. The runway is only 527 meters, 1,729 feet, long and 30 meters, 98 feet, wide. It has a 12% incline, sloping uphill from the touchdown zone to the end. This unusual gradient helps aircraft decelerate quickly during landing, but it also limits the margin for error. The runway ends abruptly at a solid mountain wall on one end and drops into a steep ravine on the other, leaving no room for aborted landings or takeoffs. Landing at Lukla is one way, only on runway 06, heading uphill toward the mountain. Takeoffs, on the other hand, are always from runway 24, downhill toward the cliff. Pilots must approach through narrow mountain valleys and have no room to go around if an approach fails. In poor visibility or high winds, this becomes especially dangerous. Weather at Lukla can change rapidly, with fog, clouds, and high winds appearing unexpectedly. Flights are often delayed or canceled due to poor conditions. Only highly trained pilots with special certification and at least 100 short takeoff and landing (STOL) missions are permitted to operate in and out of Lukla. With no navigation aids, like ILS, Instrument Landing System, and limited radar support, landings are made entirely under Visual Flight Rules, VFR. Lukla's takeoff and landing procedures are a test of both man and machine, demanding precision, timing, and nerves of steel. We follow the test flight process of the Mosquito helicopter, a single-seat, ultralight rotorcraft known for its compact design and personal use capability. Unlike larger commercial models, the Mosquito is designed for individual operation, making every stage of its flight preparation and performance unique to the ultralight category. The aircraft's efficiency and agility are what make it stand out in the realm of ultralight aviation. The sequence begins with pre-flight checks, where the pilot inspects key components including the main rotor blades, fuel system, airframe joints, and tail boom. These visual inspections are critical for identifying any structural or mechanical anomalies before takeoff. Next, the pilot enters the cockpit, which features a minimalist instrument panel tailored to essential readouts, such as engine RPM, rotor speed, temperature gauges, and fuel levels. Before ignition, the throttle and mixture controls are calibrated, and the rotor is cleared for rotation. Engine startup initiates with primer pumping and ignition. Once the engine reaches optimal idle RPM, the pilot engages the clutch system, allowing the main rotor to spool up gradually. The rotor speed is carefully monitored until it stabilizes at takeoff range. As liftoff begins, the pilot controls altitude and attitude using cyclic, collective, and anti-torque pedals. The Mosquito's lightweight frame requires constant micro-adjustments for balance, particularly during hovering and low-speed maneuvering. These movements highlight the pilot's fine motor control and the aircraft's responsiveness. Once airborne, the flight proceeds with simple circuit patterns, altitude changes, and straight-line acceleration tests. Throughout, the pilot evaluates engine response, vibration levels, and control feedback. All data collected informs future maintenance and operational adjustments. The flight concludes with a controlled descent and landing. Post-flight checks include cool-down, rotor disengagement, and system shutdown. This short but precise test flight illustrates the operational simplicity and technical discipline behind flying an ultralight helicopter like the Mosquito. In this flight training session, we observe the early stages of a student pilot's journey in the Robinson R44, a widely used light utility helicopter. This model is known for its responsive handling and is frequently used in pilot training due to its reliability and direct control feedback. The training begins with a pre-flight inspection, during which the student checks essential components such as rotor blades, fuel levels, fluid lines, and the general condition of the airframe. These steps are critical to ensuring airworthiness before ignition. Attention is also paid to the main rotor hub and tail rotor gearbox, as any irregularities in these areas can compromise flight safety. Even the smallest hydraulic leaks or belt tensions are noted and reported. Once inside the cockpit, the checklist continues with avionics, cyclic and collective control movement checks, throttle calibration, and tail rotor pedal positioning. With the instructor seated beside the student, startup procedures are initiated, beginning with electrical systems, fuel valve positioning, and engine startup via magneto engagement. Engine RPM is monitored closely during warm-up to ensure stable performance. The governor is engaged to manage throttle automatically, keeping the rotor speed within safe limits. The student also confirms the warning lights and gauge readings, ensuring all systems are within operational parameters. As the helicopter lifts off into a hover, the student practices maintaining altitude and heading, a foundational exercise for learning balance and control in a rotary wing aircraft. Hovering requires constant micro-adjustments on all three axes: pitch, roll, and yaw. The R44 sensitivity makes this phase particularly valuable for skill development. The flight continues into low-altitude maneuvering and pattern work. The student is guided through coordinated turns, climbs, and descents, while managing engine power and rotor RPM. Auto-rotation drills are also introduced, simulating engine failure scenarios and practicing emergency glide techniques, a vital part of helicopter training. During forward flight, the instructor emphasizes key points like maintaining translational lift and situational awareness. The cockpit workload increases as the student manages both navigation and mechanical systems under guidance. Each maneuver is repeated several times for muscle memory and precision improvement. Post-flight procedures involve throttle reduction, rotor cool-down at idle RPM, and shutting down avionics in sequence. This 9.8-hour training log marks significant progress in mastering the complexities of rotary flight. From hovering to auto-rotation, This foundational experience forms the backbone of future flight proficiency. A helicopter is used to place the final section of a 400-foot communication tower in Ohio. From a first-person vantage point, we follow the complex coordination between ground crew and helicopter pilot, an aerial ballet requiring extreme precision and timing. Every roll on the ground and in the air is synchronized to execute a lift that leaves no room for error. Even the smallest misalignment can jeopardize the structural integrity or create dangerous oscillations mid-air. A heavy-lift helicopter hovers steadily above the tower site as it prepares to lower the last steel segment into place. Maintaining such a stable hover at this altitude demands significant experience and a deep understanding of flight dynamics. This maneuver tests the limits of both pilot skill and aircraft performance. Before the flight, thorough planning takes place on the ground. Rigging crews inspect the tower section, attach lifting slings, and confirm weight distribution. Weather, wind conditions, and flight paths are also evaluated to ensure safety throughout the lift. Specialized rigging hardware is selected based on the section's geometry and stress points. Once the signal is given, the helicopter lifts off, towing the massive load with a long line suspended beneath the fuselage. In the air, the pilot must maintain a steady hover while compensating for downwash, crosswinds, and micro-movements from the suspended load. Continuous visual reference points help the pilot remain centered over the tower. Communication between the pilot and ground signalers is continuous via radio headsets, allowing real-time alignment. The tower workers climb to position and guide the load, using hand signals and rope taglines to control swing and rotation. As the final section approaches the top, adjustments become increasingly subtle. The pilot makes minute corrections using pedal, cyclic, and collective controls, hovering within feet of the steel structure without direct sight of the load. The margin for error narrows with each foot of descent. From this POV footage, we see how every second counts in achieving alignment. Salus Iapas. The ground team then bolts the final section into place, securing the structural integrity of the tower. Once confirmed, the helicopter gently releases the tension on the line and ascends back, leaving behind a completed 400-foot tower. The success of this operation depends not just on machinery, but on human discipline and teamwork. From a climber's point of view, this video captures the final phase of assembling a 490-foot self-supporting tower in Watts, Oklahoma, an uncommon structure with fewer than 30 of its kind across the United States. Built by Sabre Industries for a major electric utility, the tower features a massive base footprint, with leg spacing reaching 47 feet. The video focuses on the helicopter-assisted stacking operation used for the upper sections, where traditional ground-based cranes are no longer feasible. Prior to lift day, the entire project required thorough coordination, from transportation of tower segments to rigging preparation and flight logistics. The team installed lower sections using ground equipment, but for the top tiers, a heavy lift helicopter became essential. On the day of the lift, riggers on the ground prepped each section with sling assemblies, aligning center of gravity and connection brackets. Aerial insertion demanded precise synchronization between pilot and climbers stationed high above. The helicopter maintained a stable hover despite rotor wash and wind drift, lowering each segment by long line, while radio spotters guided movement in real time. Even minor misalignment could delay the process or force a lift to be aborted entirely. That's why every movement from both air and ground teams was deliberate, rehearsed, and responsive to changing conditions. Trust between pilot and tower crew was critical at every stage of the sequence. Each lift lasted only minutes, but setup and safety checks consumed hours. Once in position, tower climbers bolted flanges, checked alignment tolerances, and secured structural connections, often while suspended hundreds of feet in the air. This stacking process not only reduced ground impact, but also showcased the high level of human skill and teamwork required in vertical infrastructure projects. As the last section locks into place, viewers witness the culmination of planning, precision, and aerial engineering. The video takes us through the process of installing a new WKBD repack antenna atop a 1,000-foot tower in Southfield, Michigan. The procedure begins with a careful site inspection to ensure all safety protocols and equipment are in place for the high-altitude work. Helicopter-assisted installation plays a key role in such a tall structure, as it eliminates the need for cranes or scaffolding at extreme heights. The helicopter lifts the antenna components to the top of the tower, while the ground team carefully positions the load using long-line rigging techniques. This method minimizes the risk and complexity of manually hauling heavy parts up the tower. Once the antenna is positioned, the team secures it and performs checks to confirm it meets all operational standards. The precise coordination between the helicopter pilot and the ground crew ensures the installation process goes smoothly, with each part of the antenna safely placed. After securing the antenna, additional testing is conducted to verify the antenna's performance and adjust if necessary. This efficient and innovative method allows for minimal downtime and quicker antenna setups, ensuring the smooth continuation of broadcasting operations. Not every job takes you 1,500 feet above ground, but this one does. In this video, tower climber Kevin Schmidt ascends the now inactive KDLT analog TV broadcast tower near Salem, South Dakota. The task? Replacing the beacon light at the very top. The climb begins on a clear fall morning, with safety gear checked and communication maintained throughout. This man carefully scales the narrow steel framework, pausing at rest platforms as he nears the final section. Wind speed and structural sway are monitored constantly to ensure safety during the ascent. At the summit, he changes the bulb and secures the fixture, then takes a moment to admire the expansive view. It's a process requiring endurance, precision, and no fear of heights. In this video, tower technicians perform the deconstruction of the KWTV broadcast tower in Oklahoma City, a structure that once stood over 1,600 feet tall. This footage captures both the technical challenge and human precision required for working at extreme heights. The crew from Tower King II begins the process by removing key structural sections, working methodically from the top down. Each component is detached and lowered to the ground using high-capacity rigging systems. Safety is paramount. Harnesses, radios, and strict communication protocols are followed throughout. As weather conditions constantly shift at such altitudes, the team must adjust in real time, balancing speed with caution. Equipment is checked, rechecked, and operated under strict coordination. It's not just a job, it's a dance with gravity, where every move matters. The video pays tribute to the skilled professionals who climb these giants not only to build, but also to dismantle them, ensuring continued safety, innovation, and connection. From the clouds to the earth, it's a process driven by courage, expertise, and trust. Watch the unique process of replacing a light bulb at 300 feet above Moscow, Idaho. What would be a simple task on the ground becomes much more challenging at this height. The video begins by showing the preparation of the necessary tools and equipment. Every detail is checked to ensure safety and efficiency, as this is no ordinary job. As the team climbs into position, the process of replacing the light bulb unfolds. With precise coordination, the crew carefully swaps the old bulb for a new one, all while maintaining strict safety protocols. The task requires focus and accuracy, as the height and conditions add complexity to what would typically be a quick job. Even the smallest mistake could lead to complications at this altitude. The environment adds its own challenges, with wind and weather conditions affecting the team's work. This video offers a fresh perspective on a seemingly routine task, highlighting the extra effort involved in completing it at such an altitude.
We're good!
Replacing insulators on high-voltage transmission lines is no easy feat, especially when it takes place hundreds of feet above the ground. In Oroville, California, linemen perform this essential task on an H structure, demonstrating the precision and endurance required to maintain electrical infrastructure.
Yep.
The operation begins with a safety briefing, where each team member reviews their role and the specific hazards involved. Personal protective equipment is checked, and tools are secured to prevent any accidents during the climb.
Up. Down.
Climbing the structure requires physical endurance and attention to detail. Once at the working height, linemen carefully maneuver to access the insulators, mindful of maintaining 3 points of contact at all times.
Yep.
The removal of old
No, I need the
insulators
hook.
involves loosening hardware and safely lowering the components to the ground. New insulators are then hoisted up, aligned precisely, and secured in place, ensuring the integrity of the transmission line.
Yep. Hey, hold on a sec. Let me,
Throughout
Remove
the
this up.
procedure, communication
Yep,
between
yep,
team
yep.
members is constant, often facilitated by hand signals or radios, to coordinate movements and address any issues promptly. Environmental factors like wind and weather conditions are continuously monitored to adapt the workflow as needed. The replacement process can take several hours, depending on the structure's height and line configuration. Specialized tools like hot sticks and live line tools are used to minimize risk when working near energized components. In some cases, helicopters may be involved in transporting tools or assisting with inspections, but this operation is performed manually from the tower.
Let it go a little bit.
After installation, linemen conduct a final inspection to ensure all components are secure and aligned. Torque checks are performed to verify fasteners are tightened to the proper specifications. Once confirmed, the team carefully descends and reports back with a completed checklist for documentation. These measures are essential for preventing faults and maintaining grid reliability. Linemen often work long shifts under intense conditions, requiring not only technical expertise but also mental resilience. Even a slight misstep at these heights can lead to severe consequences, which is why redundancy in safety systems is vital. Team cohesion is developed through rigorous training and shared experience, allowing members to trust each other implicitly during high-stakes operations.
Go ahead. Go ahead. You're pulling the wrong one.
Post-operation reviews help identify lessons learned and improve future procedures. This continuous cycle of training, execution, and evaluation helps maintain the high standards expected in utility maintenance.